And this lecture will start with discussion of motion of charged particles in magnetic field. Well, I should turn this microphone in this way. So particles in magnetic field. So suppose we have magnetic field which is directed perpendicularly to the black body. And suppose we have particle with momentum p, again moving in the plane of the black body. The particle has charge p. And then what will happen? The particle will have circular orbit with radius, which is called Larmor radius. And Larmor radius equals P, momentum of particle, over E and B, the strength of magnetic field. So this is strength of magnetic field. This relation can be obtained equating centrifugal force with the force produced by magnetic field. So centrifugal force is because you have momentum p and particle tends to move along this momentum and increase the radius. In contrast, magnetic strength tends to shorten the radius. So you can reproduce this in this way. So centrifugal force is proportional to P, and this one is proportional to E and B. So this tends to decrease the radius, this increases the radius. So RB, again let me repeat, it increases if P increases, and RB decreases if B and E increases. If particle momentum is not in the same plane, which is orthogonal to the direction of the magnetic field, then particle will do spiral motion. So if magnetic field is like this, then particle will move in this way. Again with the radius, which is Larmor radius. The important point is that RB doesn't depend on the mass of the particle. So if you don't know the mass of the particle, but know what is the momentum and what is P, you know what is Larmor radius. You can use this to measure momentum of particles. And this is crucial thing, because from Larmor formula we get that momentum equals charge B and RB. So from the point of view of the experiment, this you know, RB you can measure. If you see the trajectory of the particle, you can measure what is the radius of the orbit. This you can assume in the first place that the particle has charge 1, and in most cases it works. And so using this formula, you can determine what is the momentum independently on the mass of the particle. Not only this, depending on the direction or the curvature, you can determine the sign of charge. So if you have positive charge and the particle moves along this trajectory, then for negative it will be like this. So this is plus E and this is minus E. So applying the magnetic field, you can measure momentum of particle, and you can determine the sign of the charge. So let me summarize our tools, how we are studying particles and determine their properties. I think it should be clear. I hope you have already studied these things before. But this you should remember. So that's very important. So summary of this part is the following. What we observe, and we will discuss this extensively, tracks of the particles in medium and magnetic field. So this is what we will study, because before what we have seen is just some spots, shining spots in the discovery of the electron or alpha particles or scattering of alpha particles. Here we will discuss in this part of the course trajectories of the particles and properties of trajectories of the particles and how we will measure the properties of particles observing the trajectories. So what we can do is the first to measure RB, Larmor radius, if we apply magnetic field, and that gives to us momentum of the particle and sign of charge. Then we can observe thickness of the track of the particle and how the thickness changes along the track, along the propagation of the particle. Just a second. Thickness of track. And this thickness is proportional to dE over dx, the energy loss. Remember that in the case of radiation, this is proportional to z squared, energy or momentum, divided on the mass squared of the particle. This is in the case of radiation. In the case of ionization, we have Z, the mass of the particle squared over momentum squared. So let me put here also momentum. This is ionization. And looking how the thickness of the track changes, we can determine what kind of energy loss dominates. So in the case of ionization, it's like here, the track becomes wider because the lower the energy, the lower momentum is, the bigger the energy loss. And in the case of radiation, it becomes something like this. So, once we identified which kind of the energy loss occurred, for instance, we have ionization, then measuring dE over dx, we can get the mass of the particle. Since we know what is P, so we determine momentum from the trajectory in the magnetic field. And then using these formulas for the energy loss, we can measure the mass of the particle. Okay, so use this and measure the mass. So, using these tools, we can find P, electric charge, and the mass of the particle. And in fact, already with this, we have good identification features of the particles. Let me lock the door. Questions? Okay, so now we will move to the next discoveries of elementary particles. And those discoveries have been done in cosmic rays. And let me say a few words about cosmic rays. The cosmic rays, existence of cosmic rays, which is some radiation which arrive at the Earth from the outer space, cosmic rays have been discovered in the beginning of last century. And in the beginning of last century, what people have observed spontaneous discharges of electroscopes. Who knows what electroscopes are? Probably you saw these machines in electromagnetic course and electrodynamic course before. So these are disks. I will show you the plot at some point. Two parallel disks. And when you produce friction of this disk rotating them, they turn out to be charged. And then so one is plus, another is minus. And what has been observed, of course if you connect by wire, you will see the current. But even if you have no wires here, if you have two separate plates in electroscope, from time to time you will observe discharges. Spark will be moving from one plate to another one. And the idea was that this happens because of presence of natural radiation. Natural radiation around, which produces ionization of air essentially, and then this produces discharges. So ionization means that you create electrons and ions, and of course if you have electric field between the plates, they start to move, producing current, which leads to discharges of electroscopes. The key discussion was where this natural radiation comes from. And the first idea was that this is just radiative elements in the crust of the Earth. Which produce gammas or electrons, and those particles eventually ionize the medium. Now, if you accept this, then you have prediction that ionization should decrease when you go upper and upper from the crust. So radiation decreases, ionization decreases, and the number of discharges should decrease. So, with increase of H, which is decay, over the surface of the Earth, you should observe, in this case, decrease. Decrease of radiation, and therefore number of discharges. So there were various experiments actually which led to doubt that that is the true, that the number of discharges decreases when you go upper and upper. And a final test of this idea has been done by Victor Hess. In 1912. And he used balloon. So again, you probably saw these pictures. He was sitting here and have taken with him the electroscopes and observed how discharges, the rate of discharges changes with the K of the position. So what he has observed that radiation increases with K. So radiation, and therefore the number of rate of discharges increases with age, which means that radiation comes not from the Earth, but from above. In fact, Millikan, already around this time, has proposed that actually these are protons so, and this radiation was called cosmic rays, comes from above, that cosmic rays are protons which are produced somewhere outside our atmosphere or maybe our solar system and heat the atmosphere from above, producing what we observe on the surface of the Earth. So here again, we conclude that this radiation has cosmic origin. And therefore we call these cosmic rays. So I will be very brief. I may come back to this topic later after we will discuss properties of particles, before actually I hold the lecture on cosmic rays. This is very important and still very active field already, because we still don't know precisely where these particles are produced and how they are accelerated. So the general picture is that we have the surface of the Earth, we have atmosphere, and typically it's 20 kilometers width, which is important for production of secondary of the particles. And what we have the fluxes of particles from cosmic space, and those are protons, nuclei, electrons, gamma, and neutrinos. And say in the last 10 years we really detected these cosmic neutrinos of cosmic origins. The charged particles and also gammas, they produce secondary particles in the atmosphere, and actually at high energies or very high energies there are developments of cascades even in atmosphere. And what we observe at the surface are secondary rays. So these are primary cosmic rays. And what we observe in our detectors at the surface of the Earth are the secondary. Cosmic rays produced in the atmosphere. So, let me repeat, we have gamma heating the atmosphere, and they produce electromagnetic cascades. So secondary particles, which are again gammas and electrons, but at lower energies, because energy degrade, it is distributed. We have protons and the nuclei, which produce hadronic cascades. And since we haven't discussed still these particles, but still I will say in advance that they produce more protons, neutrons, pi mesons, particles which have strong interactions. The hadrons, particles which have strong interactions. Now, as I said, all the neutrinos were detected. And neutrinos, they have first weak interactions, but then they produce secondary particles. They produce charged leptons, which then produce electromagnetic cascades, and eventually hadrons also appear. And at very high energies, and by the way, the energies of cosmic rays span over huge range from 10 to the 9, and actually there are also lower energies, of course, but what has been detected is from 10 to the 9 to 10 to the 21 electron volts. Huge energies of primary particles have been observed. Of course, we don't see these primary particles, but we see cascades developed in the atmosphere. And the sizes of these cascades are actually kilometers. So it's not a small phenomenon, although produced by a single particle. It's a huge phenomenon. We can see radiation from these cascades developed in atmosphere. And we can observe a number of particles. And sometimes the number of secondary particles can be as big as 10 to the 8 secondary particles. Of course, there is an interesting question, what is really origin, or what is really chemical composition of these cosmic rays? There are protons, and there are nuclei of different types, from light to very heavy nuclei. So we can measure this at low energies using satellites. And satellites at low energies can detect these cosmic rays, and so we can say precisely what is the nature of these particles. At very high energy, satellites cannot do, so you need to have big volumes or big area of the detector to measure these cosmic rays. And still it's open question, what are particles at this very high energy tail? So as I said, that still it's open question what precisely the source of the cosmic rays. And apparently these high energies are because of acceleration processes. So originally these particles are at lower energies, but because of certain acceleration process, they reach so high energies. And so the present understanding is, well, actually Fermi has suggested the first mechanism that these particles are accelerated in shock waves produced in astrophysical objects. And now we think that probably there are jets of material which appear from various sources like active galactic nuclei, and there are also shock waves in these jets. And in these places, there is acceleration at very high energies. At moderate energies, let's say, there are sources in our galaxy, and those are, again, shock waves which are created at collapses of the stars, and so-called supernova phenomena. I may come later to this and to discuss this in details. So what is important for us, there is a kind of costless radiation which actually reaches our detectors and originate from interactions of cosmic rays in atmosphere. Questions? Cosmic rays is part of so-called multi-messenger astronomy. which apart from these components, electromagnetic radiation, now includes also gravitational waves. So observation of cosmic ray particles, neutrinos, gravitational waves, eventually should give to us a more complete description of the space, of the universe. And maybe some of you will work on this multi-messenger astronomy. Okay. So, before we will discuss discoveries, let me still make more comments on observations of particles. So we discussed ionization and radiation. And also excitation of atoms. Atoms and molecules. This was actually G.G. Thomson saw when he discovered the electron. So these primary effects are not seen by eye and even by our detectors. So this is kind of primary effects which particle produces, right? So it produces ionization, it produces some radiation, but we cannot see them. So we need still to do something to see these primary, or to have information about primary effects. So how do we visualize this? Primary effects. There are different methods, very clever, very interesting, developed over the time of developments of particle physics. And one of the first of these effects was to use critical phenomena. When we have some system, in unstable state, so that even some small perturbation can produce big effects, which can be observed macroscopically. Therefore, in this case, primary effects act as triggers of more bigger and classical and macroscopic phenomena. So they trigger these macroscopic changes, and that's what we can see really. So trigger macroscopic phenomena. So people discuss many different system with this unstable situation and state and various critical phenomena, and some of them are related to phase transitions. So, for instance, phase transition between gas and water. That occurs at certain critical temperature or pressure. So around 0 Celsius, so the air is transformed to water, right? Gas progression, gas and liquid, or water. This is still not critical phenomena. The critical situation is when we go to the conditions when temperature is smaller than critical temperature, but still we have the gas or air. That happens, so which means that although the temperature is below 0, still we may have not condensed situation. So that is possible when we have isotropic and very clean medium. So in this case, you still can reduce temperature of your system below critical. Your gas below the temperature when it should be already condensed. And then what happens, so there is no impurities. But this system is unstable. If you have some perturbations, or introduce impurities, then the system very quickly starts phase transition and gas turn out to be the water or liquid, so you will have then the phase transition. So what I want to conclude here, that the primary effects produced by particle can actually be these impurities or perturbations which lead to phase transition. So in our example, we can create what is called supersaturated gas. Which is the gas at the conditions below critical. If particle propagates in this gas and produce ionization, so to say non-uniformities, this ionization then trigger phase transition. So we are talking here about the phase transition between gas and liquid. But there are detectors which are based on the opposite situation, with so-called bubble chambers, when we have liquid at certain conditions, at superheated conditions. But then it is converted to the gas, to the bubbles, when some impurities appear. Okay, it's not all the story. Suppose we have particle which produces ionization, and these ionization ions, the most important are positive ions in this case, and the places where ions are produced, the phase transition starts. So this is kind of the principle of work of Wilson cloud chambers. So it was invented by Wilson in 1911 and widely used in the first discoveries of elementary particles. So it uses again, let me repeat, the phase transition of air and vapor. To water. So suppose this is the medium, and actually the first Wilson chambers were very small, like this, 20 centimeters, quite small. So suppose we have this medium, gas or vapor, at T below T critical. Suppose particle crosses this medium, produces ionization around, so particle crosses, and produces ionization along the trajectory. So this triggers condensation along the places where this ionization occurs. Especially if it's positive ions. And what is important, that condensation first occurs as appearance of small droplets. So there are some small droplets in the places where ions are created, but then these droplets start to grow. And eventually all the space in the detector will be converted from gas to water, to liquid, or from vapor to water. So the first appearance of droplets of water, which then grow, and in this way the phase transition will occupy all the space of the detector. So all the idea is to make a snapshot to photo your camera before these droplets becomes very big. So droplets increase, and you see these droplets because they become macroscopic. And you can make a photo of this snapshot. But you need to make this snapshot right in time when the droplets are still not big. So they started to be formed, but not big. And therefore, you will see the track. So you'll see these droplets, track made of droplets. So, how people know when you should make a photo? Tell me. How do we know the moment when we should do the photo? Any idea? So you understand the question? So everything is nice, but you need to know precisely the moment when particle crosses your detector, and in this moment make the picture. Then you will see the track of the particle. Now, those who had already courses on nuclear physics should know this, no? Particle physics. Okay, so what people did in the early days, they just make randomly photos. They don't know, they didn't know when the particle crosses. And of course, in many of these photos, there is nothing, it's just empty. But if you are lucky, in some of these photos, you may see the tracks. And that's actually how the first discoveries have been done, just randomly. Nowadays, what we are doing, we are putting another detector here, which actually registers that some charged particle enters your main detector. So usually people are using so-called Geiger counters with very high electric tension, so that particle when processes it immediately produce discharge, and you know that particle entered. And then in this moment you switch on your camera. So you can do kind of tagging of particles which enter your detector. But in the early days, that hasn't been applied, and experimentalists were doing just randomly the photos, and in some cases, one sees the track. So now let me describe the Wilson chamber in some details. And explain how it works. Again, I have slides with this chamber, and you might find it with the new element. So the chamber had the radius. Well, actually, the radius was just 16 centimeters in the first chamber. So diameter, sorry. And the thickness was 3 centimeters. It was plate at the middle, lead plate, to observe how particles lose the energy in this plate. A plate was something like 0.5 centimeters in the first experiment. So this chamber was connected with pump. it worked in the following way. At some moment, one turned on, it produces very fast expansion and cool the air. And in this way, the air becomes overcooled at critical conditions. This is the first step. And the second, make snapshot. And experimentalists repeated this many, many times. Switch on pump, expand, cool the air, make the photon. Okay, repeat again and again and again, many, many times. And in some cases that led to big discoveries. So now let me discuss discoveries which were made using this method. Who knows what was the first discovery? Big discovery made using Wilson chamber. Yes, right. It was discovery of positron. And positron was introduced after Dirac had written his equation. And it turned out that this equation has solutions with negative energy. And then it was interpretation of these negative energy solutions as solutions which correspond to antiparticle. Now Dirac has written an equation for electron. It was also known that the mass of the positron should be equal to the mass of the electron. So now we know this is the consequence of CTP. And that was actually mentioned by Oppenheimer in 1960. The positron has been discovered by Anderson, Carl Anderson, in 1932 in Caltech. He used Wilson chamber Let me draw projection from above. This is what camera saw. So this is the chamber, and let me put here the layer for lead. And that was a 0.5 centimeters thickness. And a magnetic field was applied in this direction, and the strength of the magnetic field was 1.5 Tesla. So he used this machine and camera and made many pictures, and in one of these pictures, whole discovery was just made because at one of the pictures, Anderson saw the track of the following line. I will show you, probably you saw this, but I will show you the slides with this track. So, observations. First, since it was magnetic field, he would measure the radius, and the trajectories were not straight lines, they were bending. And using the bending, you can find what is the radius, Larmor radius. And knowing Larmor radius size, and knowing the charge, assuming the charge is 1, and knowing this B, one can find that momentum of the particle is 23 mVs. Second, he observed the curvature is in this direction, not in this, but in this direction, which actually corresponds to the plus E charge, the positive particle. The third observation was that the curvature here was bigger than curvature here, which means that particle lose the energy. Here momentum is smaller, curvature is bigger, momentum is smaller. This means that particle lost the energy here in the plate. It moved in this direction. And a loss of the energy was not small, it was something like, it was comparable with the energy of the particle in the initial state. Actually, better to say momentum. Sometimes it was momentum. Change of momentum was not small. Then you can measure here, you can measure curvature here, and you can restore what is the momentum of particle in the beginning and after the crossing the ray. Now analysis. I'm giving these details because this is kind of model of how we proceed these days with other discoveries. So that's kind of components of experimental studies and discoveries of particles. So we have observations, detector observations, and now we need to analyze. How do we analyze? In the early days it was very simple. So what is this particle X? And by that time people knew only one particle with positive charge, and that was proton. So first you can imagine that maybe this is proton. However, for proton, P is momentum 23 MeVs. The proton with this momentum is extremely non-relativistic, right? It's non-relativistic. So the mass is 968, and here is 23 MeV. So the P is much smaller than the mass of the proton. And proton with this momentum loses the energy by ionization. Right? As we studied. And dE over dx would be, I can find 8,000 MeVs over centimeter. And this is excluded because the proton with this huge energy loss would not be able to cross 0.5 centimeter layer. Clear? So, if it has initial energy, which is actually even much smaller than 23 MeVs, the proton will lose the energy in the very, very thin layer of lead insertion. So, proton cannot cross. And so we can exclude proton. So we can imagine that this is some new particle. Already this is discovered. So if I found some new particle, because it is not proton. It is not proton, we don't know. We knew by that time electron, we knew gamma. That's it. So that is already discovery of new particle. But then I can assume that this is something which has mass x and try to tune this mass in such a way to explain the energy loss here. And doing this, one can find that mx should be smaller than 2 masses of the electron. So from this picture, from the energy loss, from initial and final momentum, which are measured, one can conclude that the mass of this particle should be smaller than 2 masses of the electron. So this is consistent that mx is equal to me. So later, and by the way, the energy loss is due to radiation. So one changes the mass and see what is the dominant energy loss, and as we discussed before, knowing the energy loss, you can find what is the mass of the particle. So later it was more precisely measured, and it was shown that indeed the particle has the mass equal to mass of the electron, and that was identified as the particle with positron. This is discovered as positron. Questions?
I have one question. Will we take a snapshot of the track? Doesn't we alter the trajectory of the track?
So say again?
When we take a snapshot of the
Yeah.
track of the particle, doesn't we alter this trajectory?
Why? Why we should alter? So that's what was seen on the photo. So it was seen that actually that is made of these droplets, right? So that was, but when you do photo, you do not influence everything in any significant way. Just the photo showed this the lines which are made of droplets. More questions? Okay. So we move to next discovery, which is discovery of muon. Which is one of the fundamental discoveries which led in the basis of creation of the Standard Model. And we use symbol mu for its value. Muon has been discovered again by Carl Anderson. And Ledermeyer. In 1966. By the way, I didn't mention before, but the source of positron, which Anderson has been discovered, that was the secondary of cosmic rays. Also here, the source of these new particles was cosmic rays, secondary cosmic rays. Detector was again built in chamber. What was the observation? Observation was a track but with very small curvature. And the curvature didn't change much after crossing the left plate. So, of course, this corresponds to charged particle. Which penetrates strongly. This is because the change of curvature is small. Delta T is smaller than momentum, in contrast to the case with positron. So the energy loss is small. And then measuring still these curvatures, it was found that momenta of these particles, and here they observed several events of this time, were few multiplied by 100 MeVs. So it's a higher energy event, and 200, 300, 400 in this range. So that's what has been observed. And finally, they observed the events with sign plus and minus. So one of the first events was again with charge plus. So let's take this plus. Then the question is, what is this if x again? And one possibility that is again proton. For this momenta, proton is also non-relativistic. And therefore it should be large energy loss. And also the tracks should be thicker. Also one can not only measure the change of the curvature, but also see what is the thickness of the track. Already this gives you what is dE over dx. The thickness is proportional to dE over dx. And it is clear that the energy loss is small, both here, but also here. Here you expect in the plate very big energy loss. And so the proton doesn't match this picture. The second is X positron. Maybe this is the positron. The positron with these energies is highly relativistic, right? So for positron, P is much bigger than the mass of the positron. Highly relativistic. And it loses the energy by radiation. Remember, critical energy is something like 7 MeVs, and here we have several hundred MeVs. So it's above the critical energy. The main energy loss is on to radiation. And again, the positron with these energies cannot penetrate this plate, and even those who manage to penetrate will have very big loss of the energy, so you would see something like here, like this, but then it should be like this. Very big curvature. So that also doesn't work. Too big energy loss is expected. So this already tells you that again we have discovered some new particle, and in the case of, as in the case of positron, we can imagine that this particle has some mass mx, and try to find what is the value of mass mx which fits the observed event pictures. So what has been concluded that the mass of this particle should be something like 1/10 of the mass of the proton, 10 times lighter than the proton. That is around 100 MeVs. In this way you can explain the picture, the properties of the events. So what you are doing, you are scanning different values of the masses, starting from proton mass, start to reduce this mass, and with this reduction of the mass, the energy loss becomes smaller and smaller, because first it is I, so it becomes smaller and smaller. Because remember, ionization energy loss is proportional to the mass of the particle. And then you can go from the side of the electron, increase the mass of this particle, which is bigger than the electron. Then in this way, again, you will reduce the energy loss, because in this range of light masses, around 1 MeV, the main energy loss is radiation, and with increase of the mass, this radiation, the energy loss decreases. So when you go from the proton and from the electron masses, reducing the mass of the proton or increasing mass of instead of electron, then the energy loss decreases, and then you find what is really the mass of the particle which produces absorbed energy loss. Later, it was found that this particle decays. So let me discuss muon decay. And events have been observed on the following type. So that track has been identified with muon. And then you saw the track of this type. So if you are experimentalist and doing this type of the, and finding this type of the events, how you would interpret this event? So here, clearly you produce some particle which is, of course, of smaller energy and therefore momentum, and therefore it has bigger curvature. Also clear that something else is produced here. So, because you have no kind of energy momentum conservation in this vertex, it should be something else. This track was identified with the track of electron. What has been observed, and several events of this type have been observed, that the energy of electron changes from one event to another one. Therefore, the electrons have what we call continuous spectrum. As in beta decay. So which means that what we see in this type of the pictures is transition of muon into electron plus not just one neutrino, but two neutrinos. Why? So at that time when people saw some energy loss here, as it is here, they immediately blame neutrinos, so probably neutrinos are emitted. It's actually an observation was that muon go to electron plus energy loss plus momentum loss. So that's what has been observed. And once this type of the events are observed with energy disappearance and momentum disappearance, the first idea is that in the interaction, that also neutrinos are emitted. So these are events with missing energy and momentum. Now, what is interpretation? Let me repeat this. The interpretation of these events, so that's what has been wrapped up. So we go to P plus missing energy and missing momentum. So now interpretation. The interpretation is again, this resembles beta decay, is that missing energy and momentum due to neutrino. And the second, that actually two neutrinos should be produced. So this event looks like charged particle moves, loses the energy, stops, and then decays. If you have just one neutrino, then in all the events, electron should have the same energy, which is roughly half of this particle. Clear? Let me put it again. Mu stops and decay. So if muon stops and it has two body decay, so if muon decay into electron and neutrino like this, these particles are very light. And in this case you expect that the energy of electron should be just 1/2 of the mass of the muon, and therefore should be nearly the same in all events. The fact that continuous spectrum has been observed, so the energies of electrons in different events varies substantially, means that you need to introduce some other particle, and so that in this case electron and these particles share the energy, and you can satisfy energy momentum conservation for different values of the electron energy. Clear? So, we arrive at the conclusion that we need to have mu plus mu. Clear? Again, if you would have just two particles in final state, that energy of electron in all the decays should be fixed. And it is approximately half of the mass of the muon. This way we would have muon decay rest and configuration like this. We have muon and neutrino. And energy momentum conservation would tell us that the energy of electron should be approximately half of the mass of the muon. And the energy of neutrino also should be approximately half of the mass of the muon, just from energy momentum conservation. So in this case, the energy conservation means m mu equals energy of electron plus energy of neutrino. And since both particles are light, we satisfy also momentum conservation because particle is at rest, and then the momentum should be. Agree? So if you introduce two neutrinos and they have spins 1/2, this is 1/2, this is 1/2, then from angular momentum conservation, this means that the spin of muon should be semi-integer. And the simplest possibility that spin of the muon is 1/2, and that was confirmed by some other measurements too. So let me start to discuss the theory of muon decay. We will continue in next lecture tomorrow. And see, now we make another step in construction of the standard model. So what we have, muon in initial state, which is transformed into electron, neutrino, and another neutrino. That is similar to beta decay, in which we have transition of neutron into proton, electron, and neutrino. Right? So what is interesting that electron and neutrino pair appears here and it appears here. So we have mu E pair, which appears in both cases. And you see again idea of analogy. Is very fruitful. We can imagine that this pair has the same mechanism of appearance as in beta decay. So it's produced by current made of neutrino and electron fields. So mu and E form current. And so we can write Hamiltonian responsible for beta decay. The Hamiltonian responsible for beta decay, in analogy with what we had in beta decay, can be written immediately. It should be some 4 fermion coupling, which I put here G mu. It is not necessary that it coincides with Fermi coupling constant. Then we have current which appears in beta decay, and I assume that actually the same current as in beta decay works here. And then from Lorentz invariance, I will write mu mu, the rest, is mu, 1 minus gamma pi mu. So, first of all, I'm writing this in the presently known structure form. So, by the time when the theory has been written, it was not known that the parity violation in this structure was not known. Second one, so we have the first current. And again, we can imagine that as in the beta decay, where we have current between neutron and proton, we have current which actually describe transition of muon and neutrino. So in a sense, here muon is analogy of neutron, and proton is analogy of the second neutrino, or second neutrino is analogy of the proton. And so we have the second current formed by muon, and again let me write this in modern terms. This is muon neutrino. We will discuss later how people distinguish or establish that here we need to write not just second neutrino, but neutrino of another type, which differs from electron neutrino. So let me summarize that we have here Hamiltonian, which has Lorentz invariance, and we have written this in the form which is analogous to beta decay. So we will discuss different processes and construct Hamiltonians for different processes. Eventually we need to sum up all these Hamiltonians. So all the theory is the sum of Hamiltonians which describe different processes. Why? Because Hamiltonian is energy. Energy is an additive quantity, and therefore if you have different type of the interactions, you need to sum up. So the total Hamiltonian is the sum of the Hamiltonians responsible for different processes. Of course, if they are not reduced one to another, like Hamiltonian responsible for beta decay also give for us inverse beta decay and scattering of neutrino. But here is something new, because new particles are involved here, and we need to write another Hamiltonian part. And this is the Hamiltonian, which presumably describes beta decay. Of course, we need to check all the things, which means to see what are the consequences of this Hamiltonian and convince ourselves that this is true distribution. Questions?
I have a question. Can you hear me?
Yes, sure.
So I'm confused with how do we identify the charge of the particle? So is it when it's moving along the magnetic field, and in opposite to the magnetic field, we can differentiate it's charge, positive charge or negative charge?
So, yes, determining the charge using a magnetic field. If you have particle and you have magnetic field, then positively charged particle will go in this direction and negatively in this. So, for instance, if E plus go in this direction, then E minus will go into this direction in the magnetic field. And knowing the charge direction of the magnetic field, and then knowing curvature of the trajectory, you can say what is the charge of the particle.
Thanks.
So everything is clear? So anyway, you can send me questions by mail if you then think more and find out that something is not clear. Okay, then see you tomorrow.